Good evening, dear students. Yes, good evening, Prakash. Mamata, good evening, Gaurish, Vaishnavi, Harsha, Patil MK, Sushma. Good evening, everyone. So, in the last session, we discussed regarding the concept of image formation, right? Image formation by spherical mirrors. We discussed the case studies also, okay, by concave mirror as well as by convex mirror. So we studied various case studies. So what will happen when a ray of light passes parallelly to the principal axis? So one spherical mirror is there, okay? And this is the principal axis. Fine. So if a ray of light passes to the principal axis, what will be the reflected light? The refracted ray of light will be passing through what? Yes, anyone? Anyone? The reflected ray of light will be passing through be fast. Very good. Malik answered it. Principal focus. It will be passing through principal focus. Suppose if a ray of light, okay, suppose if a ray of light passes through, if a ray of light passes through principal focus, incident ray passes through principal focus, then what will be the reflected ray? Reflected ray ಯಾವ ರೀತಿ ಇರುತ್ತೆ? Anyone? Yes, for the first case study, principal focus is the right answer. So when an incident ray itself passes through the principal focus, okay, so then where will be the reflected ray? How the reflected ray will come? Principal axis is right. Very good. Prabhavati answered it. It will be parallel to the principal axis. And then the third case study was when the incident ray passes through the, when the incident ray passes through the, so this is the principal axis, when the incident ray passes through the center of curvature. So this is incident ray. What will be the reflected ray? Where will be reflected ray? Yes, where will be the reflected ray, my dear boys and girls? Pola. The reflected ray will be in the same path, okay, but in opposite direction. Okay, so this is about the most important case studies. Fine. So today we are going to start with the other concept of light. So till now we discussed regarding reflection. Howda? Just a minute. Yes. So today we are going to discuss regarding the concept of refraction, the other phenomena, or we can say the other property of light, refraction. Reflection means what? Bouncing back of light. Okay. So reflection means when a ray of light strikes the surface, that is, strikes the reflecting surface, it bounces back from the surface. So this is called reflection. Refraction means what here? It includes mediums. In Kannada, we will call it as madhyamagalu. See, when a ray of light travels from one medium to another. One medium to another medium. So here the medium refers to what? Here the medium refers to air. Medium refers to water. It might be vacuum also. It might be anything. Okay. So air, water. So these all are the examples of what we can say is the medium. So when the light will pass from the one medium to another medium, there will be change in its direction. The light ray will bend. Okay. So see here, when light travels obliquely from one transparent medium to another. So the medium should be what? Transparent medium. Okay. It should not be a non-transparent medium. Okay. Opaque medium. It should not be opaque. Okay. So see here, when light travels obliquely from one transparent medium into another, it gets bent. This bending of light is called as what? Refraction of light. Okay. So see here, you can see when light travels from rarer medium to denser medium. So what do you mean by rarer medium? Rarer medium means where the molecules of the medium are moving freely. Okay. Are at far distances. The distance between the molecules of the medium is very large. Okay. Denser medium means what? The distance between the molecules of the medium is quite smaller. So this is called denser medium. So when we compare air and water, can you tell me which is a rarer medium? So here rarer medium andre enu? Kanagalu or the molecules of the medium should be freely moving. They should be far from each other. So can you tell me among the air and the water, which is the rarer medium? Yes. This is English medium session. Kannada medium sessions will be from Thursday. Okay. Very good. Savita, Devraj answered it. Air is a rarer medium. Water is a denser medium. So when a ray of light travels from a rarer medium to a denser medium, it bends towards the normal. So here you can see this is a medium, this is a rarer medium, and this is a denser medium. So the light ray is traveling from rarer to denser. So that is why it is near to the normal. This is a normal, a perpendicular drawn to the surfaces of the medium. Okay. So it bends towards the normal. Fine. So when a ray of light travels from denser medium to what we can say rarer medium, it will be away from the normal. See here. It is away from the normal. Okay. So the angle between the normal and the reflected ray will be more when it travels from denser medium to rarer medium. You should know this. Okay. Now, so this you can perform at your home only, a simple experiment to show the refraction. See here. This is a pencil which I took. Okay. So consider this as a ray of light. Okay. So, and this is in the air now. So, if from the air, it is incidenting through water. So, when you see it correctly, okay, observe it properly, we feel that this is one pencil and inside we have one more pencil. Just observe it correctly. Okay, we feel that we have two pencils together. Okay. Yeah. So, like this, see. You feel that you have two pencils. But what happens here? We have only one pencil. As the ray of light is traveling from the air to the water, the light showed what? The bending phenomenon. The light showed the bending phenomenon. Okay. So that is why here it appears two pencils. Here it is appearing two pencil. So this shows the best example for what we can say is refraction. Now, let us consider how refraction occurs actually through a rectangular glass slab. So whatever you are seeing here, this is a rectangular glass slab, which is rectangular in shape and made up of glass. Okay, very good. Now, see, observe the diagram carefully. When a ray of light passes through a rectangular glass slab, it gets bent twice at the air glass interface and glass air interface. So when the ray of light passes through for example, let us consider this as a rectangular glass slab and this as a ray of light. So ray of light is coming from the air, entering to the glass slab and then again going to the air. So here we have air glass interface and here we have glass air interface. So from here it should go na glass air interface. Okay. So 2 times refraction occurs there. See here. See, this is an incident ray what you are seeing. Okay. So from the air, it struck the glass surface. So it got bent. So this is a refracted ray what you are seeing. Okay. This refracted ray strikes this surface, this glass surface and again bends via the air medium. Again gets bent in the air medium. So this reflected ray acts as incident ray for this surface. I hope you understood. This reflected ray, ಇದೇನು ಇದರಿಂದ ರಿಫ್ಲೆಕ್ಟ್ ಆಗಿ ಬಂದಿದೆನೋ ಈ ಒಂದು ರೇ ಏನಾಗಿದೆ ಈ ಗ್ಲಾಸ್ ಸರ್ಫೇಸ್ಗೆ ಇನ್ಸಿಡೆಂಟ್ ರೇ ಆಗಿ ಇನ್ಸಿಡೆಂಟ್ ರೇ ಆಗುತ್ತೆ. So this incident ray, that is this reflected ray, again will go refraction, okay, and it is bent away from the normal. Why it is bent away from the normal? Glass is a rarer medium. Sorry. Glass is a denser medium, right? Air is a rarer medium. So, when a ray of light passes from denser to rarer medium, it bends away from the normal. So, this is a normal. Where we have to draw the normal between the two surfaces. ಎರಡು ಸರ್ಫೇಸ್ ಇಂಟರಾಕ್ಟ್ ಆಗ್ತಾವಲ್ಲ ಆ ಪೊಸಿಷನ್ಗೆ ನಾವೇನ್ ಮಾಡಬೇಕು ನಾರ್ಮಲ್ ಹಾಕಬೇಕು. ಓಕೆನಾ? Fine. So, here we can say that this reflected ray undergoes refraction and here we will get what? One more ray which is called as emergent ray. No doubt this is also a refracted ray, but as it is completely emerging out, as it is completely coming out from the glass slab, it is considered as emergent ray. Okay. So this is how the refraction occurs. And when you see this incident ray is there, no? This incident ray is coming from air, that is from rarer medium to glass, which is denser medium. So when light travels from rarer to denser, it will bend towards the normal. It will bend towards the normal, as you can see. See this angle and this angle. So obviously this angle will be more. Why? Because it is traveling from denser medium to rarer medium. Okay. Now, so this is about the refraction through a rectangular glass slab. Very, very important. When they ask, you have to explain it through the diagram. Okay. Next. Next we have is laws of refraction of light. Laws of refraction of light. Before that, before moving to the laws of refraction of light, can anyone tell me the laws of reflection? Can anyone tell me the laws of reflection of light? Let me write here. Laws of reflection of light. Can anyone tell me? Which is the first law of reflection of light? Yes. Laws of reflection. Which is the first laws of reflection? Very good. Uma Shankar answered it. Angle of incidence will be equal to angle of reflection. Then which is the second law of reflection? Dhruva answered it. Then Tabassum answered it. Uma Shankar, Lokesh, Sinchana, Triveda, Netra, Usha. Then what is the other second law of reflection? Uma Shankar. Okay, the incident ray, reflected ray and the normal lies in the same plane. Same way we have laws of refraction of light. Okay, so here the incident ray, the refracted ray and the normal to the interface of two transparent media at the point of incidence all lie in the same plane. So when you just consider this, when you just a minute. See, the incident ray, the refracted ray, and the normal at the point of incidence lie in the same plane. Next, we have the ratio of sine angle of incidence to the sine angle of refraction. Refraction. Okay, so sine angle of incidence will be represented as sine I. Okay, and then sine angle of refraction is represented by sine R. So the ratio of these two will be always constant. That constant is called as what? Is constant for a given pair of media. See, sine I and sine R will be constant for glass and air. It will be constant for air and water. Okay. So this is called as what? Snell's law of refraction. So what is Snell's law of refraction? Sine I divided by sine R is equal to constant. So regarding the sign, you will learn in the mathematics. It is a trigonometrical word. Okay. Then refractive index. We have refractive index. The absolute refractive index of a medium is the ratio of speed of light in air or vacuum to the speed of light in the medium. So suppose I will consider a rectangular glass slab. Here we have air medium. Here we have glass medium. Okay, the ray of light is traveling from air to glass. Okay, so here the speed of light in the air to the speed of light in the medium. The medium may be water or a glass. Okay, so that will give us what? Refractive index, which is represented by N. Okay, which is represented by N. So the relative refractive index of medium 2 with respect to medium 1 is the ratio of speed of light in a medium 1 to the speed of light in medium 2. So refractive index, suppose we will consider air as a first medium, glass as a second medium. Okay, so the refractive index of the glass, that is second medium, with respect to first medium is equal to speed of light in medium 1. So what is in medium 1? Air. Speed of light in air divided by speed of light in glass. Same way, if the medias is air and water, speed of light in medium 1, that is air, speed of light in water. Like that, we should calculate the, what we can say is, refractive index. Suppose if the refractive index, or we can say if the first medium, if the medium 1, if medium 1 is air, then it is written as N is equal to C by V. What is C here? It is the speed of light in air. C represents speed of light in air. Okay. If in most of the cases, medium 1 will be what? Air. So that is why it is written as C by V. Okay. So can you tell me what will be the speed of light in air? Can anyone tell me what will be the speed of light in air? Very easy question. Speed of light in air. Anyone? Yes. Is it 1.3? I'm not asking refractive index. I'm asking speed of light in air. Okay, find me and tell me tomorrow. Speed of light in air. Okay. Then we have is spherical lenses. So before we learned regarding spherical mirrors, today we are learning regarding spherical lenses. So what is the spherical lenses? So here, a spherical lens is a transparent material which is bounded by two surfaces, one or both which are spherical. A lens is a material which is bounded by two surface, okay, two surface, what you can say. So among two surface, both will be curved, or sometimes one will be spherical or curved. Okay. Especially we have two main types of spherical lenses. The first one is a convex lens. The second one is a concave lens. Convex mirror, convex lens, concave mirror, concave lens. So here it is thicker in the middle and thinner at the edges. So it will be like this. It will be made up of two spherical, two convex mirrors. Okay. So it will be thinner at the edges but wider or thicker at the middle. Same way, the concave lens is made up of two concave mirrors. Okay. So which are thicker at the edges, which will be thicker at the edges. Okay. Thicker or wider, and narrower. Okay. Narrower at the middle. So here, thinner in the middle and thicker at the edges. Then, so the rays of light parallel to the principal axis. So let us consider this. Okay, and this is P. P means what here? The center of lens is called as P, that is pole. Fine. So a straight line passing through the pole is called as what? And focus is called principal axis. So here you can see the rays of light which are passing parallelly to the principal axis. So after refraction, see, it is not reflection. Reflection ಅಂದ್ರೆ ಈ ರೀತಿ ವಾಪಸ್ ಬರ್ತಾ ಇದ್ವು ರಿಫ್ಲೆಕ್ಟೆಡ್ ರೇಸ್ಗಳು, ಹೌದಾ? ಬಟ್ ಇಲ್ಲಿ ಏನಾಗಬೇಕು? ರಿಫ್ರಾಕ್ಷನ್ ಆಗಬೇಕು. ರಿಫ್ರಾಕ್ಷನ್ ಅಂದ್ರೆ ಏನು? From one medium, when light travels from one medium to another. See, the light is traveling from air to the lens, that is glass material. So it bends here. It bends because change in medium. So this is called refraction. So after refraction, you can see all the refracted rays, okay, all the refracted rays will meet at a point. This point is considered as principal focus. Fine. In same way, in concave lenses, when a parallel beam of light is incident, parallel to principal axis. Okay. After refraction, we will get the rays like this. We will get the rays like this. When these rays are dragged back imaginarily, they appear to come from a point. They appear to come from a point and spread. That is why these are diverging lenses. But here what happens? All the rays are coming and meeting at a point. These are converging at a point. So these are called as converging lenses. Convex lens, converging lenses, concave lens, diverging lenses. Now we have refraction by spherical lenses. So how we studied the case studies in spherical mirrors, no? Like that only we have case studies in spherical lenses also. The first one is refraction by spherical lenses. The first case study, in a convex lens, when a ray of light parallel to the principal axis after refraction passes through the focus on the other side of the lens. In a concave lens, it appears to diverge from the focus on the same side of the lens. So here you will get confused. See here. So as I told, lens means what? It is made up of two spherical mirrors. So convex lens, let us consider convex lens. This is one convex mirror. This is another convex mirror. This is another convex mirror. So both convex mirrors makes the convex lens. Okay. So here the center of the lens is not called as pole. So here center of mirror, we used to call it as pole. But here the center of the lens, we will call it as optic center. It is called as what? Optic center, and it is represented by O. Listen carefully. Simply don't message unnecessary things. Very, very important concept. If you don't understand the basic, you will not get the in-depth knowledge of it. So the center of the lens is called optic center, which is represented as O. And a straight line passing through the optic center is called as what? Principal axis. Okay. Now, let me clear you. So this is a convex lens. The center is called as optic center, which is denoted by O. Okay. Now, through this, what happened? Through this, a line is passed. A straight line is passed through the optic center. Okay. So that straight line is called as what? That straight line is called as principal axis. That straight line is called as principal axis. Okay. Next. So as I said you, the convex lens is made up of two mirrors. So, two mirrors. One mirror will be having one focus, one principal focus. Okay. Like that. See here. Here we will be having the focus of, principal focus of this side mirror as F1 and 2F1. That is twice of F1. Same way here, F2. So this is the principal focus of spherical mirror 2 and 2F2. That is twice of F2. So what is F2, F1? So these are nothing but the focal length, what we can call. Focal length, what we can call. This is a focal length. Just a minute. That is the length between the optic center and the principal focus. Now, let us proceed with the case study. See here, this is a principal axis. This is the optic center. F1, principal focus of this mirror. F2, principal focus of this mirror. Okay. So, when a parallel ray of light sorry, when a ray of light parallel to the principal axis passes through the lens, okay, so the refracted ray, so this is a refracted ray, the refracted ray after refraction aadmele passes through the principal focus on the other side. So this is one side of the lens, this is other side of the lens. So it passes through the focus of the other side of the lens. Same way, in a concave lens, so here you can see in a concave lens, when a parallel beam of light travels, which is parallel to principal axis, okay, it gets refracted. This is a refraction. So when you just drag the refracted ray, imaginally drag the refracted ray, it appears to come from the point which is on the same side of the lens. So incident ray yav side in the bandideno, ade side alliruva principal focus in the refracted ray bandiratte. Okay, but here it is formed on the focus of the other side of the lens. Here it is formed or it is refracted from the focus of the same side of the lens. Okay, so this is about the first case study. Next, the next case study is, okay, this next case study is when a ray of light, passes through focus. Okay, passes through focus. This is the second case study. So in convex lens, as you can see here, this is an incident ray which is passing through focus. So after refraction, that is after bending, it is parallel to the principal axis. The refracted ray is parallel to the principal axis. Same way, in a concave lens, when a ray of light directed, so see, this is a ray of light. Okay, so this ray of light is directed towards, it is not coming from the principal focus, it is directed towards the direction of principal focus. So when it is directed towards the principal focus, direction of principal focus, the refracted ray appears. So when you see the refracted ray, here also, it will be parallel to the principal axis. So in the second case, when a ray of light passes through the focus, okay, usually the refracted ray will be parallel to the principal axis. Fine. Next case study is, okay. In a convex lens and a concave lens, a ray of light passing through the optical center. So as I said, when a ray of light passes through the optical center, it goes without deviation. So there is no refraction occurs. It will go in a straight line only. No refraction occurs. Okay. Next. Yeah. Now we have images formed by the convex lens. One by one case studies we will learn. Images formed by the convex lens. So this is the object. Okay. So when the object is kept at infinity. So what do you mean by infinity here? It is kept at a far distance from the lens. We don't know the exact distance. So when the object is kept at infinity, the image is formed at the f2. F2 means what? Principal focus on the other side of the lens. On the other side of the lens. So see here, this is a principal axis, what you are seeing. Okay, this is a principal axis. So the parallel beam of light from the object are incidenting on the lens. So here they are undergoing refraction and they are meeting at a point that is nothing but a principal focus. So when you see the image, This image is diminished, means what? Very small. Diminished means very small, point-like. Real means what? It is obtained on the screen. We will watch the video regarding this. It is obtained on the screen and it is inverted. Inverted means what here? Here you have an object. This is the head of the object. This is a leg of a object, AB. But the image will be formed like this. The head will be at the up, the legs will be at upper side, the head will be at lower side. So inverted image. Okay. Next case study is when the object is beyond 2f1. 2f1 means what? The distance between optic center and 2f1 is nothing but our radius of curvature. So sometimes 2f1 is considered as center of curvature also. So the lenses will be having two centers of curvature. Okay. See here. Let me clarify you. 2f1, 2f2 ಯಾಕೆ ಬಂತು ಅಂತ ತುಂಬಾ ಕನ್ಫ್ಯೂಸ್ ಆಗ್ತೀರಾ. ನಾನು ಹೇಳ್ದಾಗೆ lenses are made up of two spherical mirrors. One spherical mirror will be having its center of curvature. Okay. The other spherical mirror will be having its center of curvature. And this mirror will be having its principal focus. The mirror 2 will be having its principal focus. Okay. So why we will not name it as C1 and C2? Because, and this is an optic center, the center of the lens. So when we measure the distance between optic center and the center of curvature, it appears to be twice of focal length. That is, this is F2 I have written. Okay. So twice of focal length means it appears to be double than this distance, that is O into F2. This is O, this is F2, this is C2 we have written. So this is what? Let us take 2 centimeter. Fine. So OC2, this distance, this is this distance OF2 appears to be 4 centimeter, which is double than which is twice than the what? F2. So that is why we will write 2F2. Same here, F1. OF1, let us consider 3 centimeter. So when we measure OC1, it will be 6 centimeter. That is double than the F1. So that is why instead of writing C1 and C2, we will write 2F1, 2F2. Understood? Because it will be the same value. Now, coming to the second case study, when the object is beyond 2F1, that is similar to beyond center of curvature. Okay. Then where the image will be formed. So you can see here, this is a one ray of light which is coming parallel to the principal axis and it is getting refracted. And this is another ray of light which is passing through the optic center and it will pass like that only. It will not bend. Okay. So both the refracted rays will meet at a point. So if we see where the image is formed, the image will be formed between F2 and 2F2. And it will be inverted, that is ulta, and it will be diminished, smaller than the object, and it will be real, that is, it is obtained on the screen. Okay, then next we have is, okay, so when the object is beyond 2F1, okay, so the image is formed between F2 and 2F2. Which is the first case study, my dear students? When the when the object is kept at infinity, the image is formed on the principal focus of other side of the lens. The next one is when the image is kept beyond 2F1, that is nothing but similar to beyond the center of curvature of one of the mirror of the lens. Okay, the image is formed between f2 and 2f2, that is on the other side of the lens. Next we have is when the object is at 2f1. So at 2f1 we are keeping the object. Okay, next. Okay, Lakshmi Harish, why the second line is straight? So while explaining the case studies, I explained you, Lakshmi. See here the second line is there, no? It is passing through what here? It is passing through the optic center. Any ray of light which is passing through the optic center will not be, what happens? Will not be bending, will not be changing its direction. It passes in a straight manner, okay, without changing in direction. That is why it is straight. I hope your doubt is clear. Please message if your doubt is clear. Next we have is, see the ray diagram properly. One ray of light is acting parallel to the principal axis and it is bending and meeting or passing through the F2, right? The other thing is, one ray of light is passing through the optical center and it is passing as it is without any deviation, change in direction. So both the refracted rays are meeting at a point. They are meeting where? They are meeting at 2f2. See, the object is kept at 2f1. That is at the center of curvature of one of the mirror of a convex lens. The image is formed at what? 2f2. That is nothing but center of curvature of other mirror which is a part of a lens. So when you see here, the image is inverted, ulta, right? And it is real, that is obtained on the screen. And it is, what we can say is, quite same size of the object. Okay, there is no diminished or what we can say enlarged image. Okay, next we have is when the object is between 2f1 and f1. Students who did not attend previous sessions, especially light chapter, ಇವತ್ತೇ ನೀವು ಅಟೆಂಡ್ ಮಾಡ್ತಾ ಇದ್ರೆ ಅಥವಾ ಮಧ್ಯದಲ್ಲೇ ಬಿಟ್ಟು ಮತ್ತೆ ಇವತ್ತು ಅಟೆಂಡ್ ಮಾಡ್ತಾ ಇದ್ರೆ, you will not understand this concept because yesterday's class was very, very important and it had the basics. Understood? If you missed yesterday's class, please do watch yesterday's class first, then attend this session, then watch this video. Then the doubts will be clarified. Okay? Then, see, when the object is kept between 2f1 and f1, one ray acting parallel to the principal axis, so the refracted ray is passing through the focus. One ray is passing through the optic center, so the refracted ray is not changing its direction. And the image is formed where? It is formed beyond 2f2. And when you see the image, it is enlarged. That is, it is bigger than the, what do you mean by enlarged? It is bigger than the object. It is real. That is, it can be obtained on the screen, right? It is inverted. As I said, ulta. All right. Next one, next case study. When the ray of, when the object is kept at f1. So first we kept what? At infinity, right? So the object, the image was formed at the focus on the other side of a lens. Then we kept where? Beyond 2f1. Okay. Then we kept between 2f1 and f1. Now we are keeping the object at f1. So when the object is kept at f1, the image is formed at infinity. At somewhere at a very far distance, the image is formed. The image will be inverted, real, and it will be enlarged. Means very, very big than compared to the object. Next case study is when the object is kept between optic center and F1. Optic center. O means what here? Optic center and F1. So the image is formed on the same side of the lens. It is enlarged, virtual and erect. See here, this is the object, right? So observe the laser point. This is the object. Fine. So one ray of light acting parallel to the principal axis, and we got the refracted ray which is passing through the focus. One ray of light is passing through the optic center, and we got the refracted ray here only in the same direction. So when we, pull them, when we pull these both refracted rays, they appear to come from a point. Okay, So when we drag this refracted rays, they will meet at a point. So at that point, the image will be formed. The image will be very enlarged, that is very bigger than the object, but it is virtual, means it is not obtained on a screen. It is formed inside the lens only, and it is erect, means what? Straight, not inverted. Means AB is there. No, here also in the image AB will be there. It is not BA. The arrow mark is right like this, pointed upwards. So the image arrow mark is also pointed upwards. So it indicates erect image. Okay. Now, let us watch a very beautiful and video on this case study of concave lens. If you watch this clearly and understood this video, then you can draw the ray diagrams very easily. Okay, please do watch the experiment video. Okay, don't get disturbed. Stop commenting simply or chatting simply, and watch this video now. Okay, I will be explaining in the middle. Just a minute. Okay, just a minute. Image formation by convex lens. Okay, by convex lens. Materials required, we want lens holder. Yesterday we saw concave mirror experiment. This is convex lens experiment. Then we have screen. Okay. Then we have candle, a source of object. Okay. A white chart paper we want to mark focus, principal, 2 F1, F1, F2 like that. So here you can see how they have arranged as F1 they have kept at 20 centimeter from the lens, to F1 at 40, because it will be double than the F1. Okay. So the lens is at 40 centimeter from 2F1. Same way, F2 is also 20 centimeter. 2F2 is 40 centimeter. So like this, the arrangement of the experiment is done. First, light the candle, and we have to study each and every case study of convex lens. So here you can see when the object is placed very far. Means what? When the object is placed at infinite distance. Okay. Now see. The image is obtained at F2. Okay, where the image is obtained, it is obtained at F2. Okay, see there. So it is highly diminished, that is small. Fine. Just a minute. Yeah, see, it is very small, right? Then that is why highly diminished. Real, why? Because it is obtained on a screen. Inverted, that is ulta, right? And where it is formed at F2. Next case study. When an object is placed beyond 2F1. See, beyond 2F1, we are keeping the object, not the lens. And just to move the screen. Okay, see here. So where the image is obtained, see it is inverted image, right? And here you can see diminished, that is smaller than the object. Real, obtained on a screen. Inverted, that is ulta, here you can see. And where it is formed between F2 and 2F2. Where we kept the object beyond 2F1. Fine. Then the third case study, object at 2F1. We are keeping the object at 2F1. Okay. So now see, the image is formed at, where the image is formed? The image is formed at 2F2. See, here you can see the inverted image. Okay. And the size will be almost same of the object. And it is obtained on a screen, real and inverted, where it is formed at F2. Okay. Next case study we have is, see, case 3 in night mode. How is the image? At F2 it is formed. Case 4. When the, what is that? When the object is kept between F2 and 2F2. F2 and 2F2. The image is formed beyond 2F2. Object is kept between F1 and 2F1. Okay. And the image is formed beyond 2F2. So here you can see the image. It is quite larger than the object. It is real. It is inverted. And it is formed beyond 2F2. Okay, see this beautiful image. Then we have is, then we are keeping the object at F1. So when we keep the object at F1, okay, so the image is formed at infinity. Here you can see. So beyond the chart only, beyond the white chart only, this image is formed. Means it is formed far from the lens. So that is why at infinity. And it is obtained on the screen. So it is real. It is enlarged. That is very, very big than compared to the object. And it is inverted. Okay, it is not straight. Okay. See, real, enlarged, very far. This is the image obtained when we keep the, what we can say, object at F1. Now we are keeping the object between F1 and O. That is optic center. F1 and O. So see where the image is formed now. No image on a screen. So you can see, you will ask me, ma'am, there is the image because the paper is being, something light is appearing on the paper. So light is appearing on the paper. Okay. It is just nothing but a brightness of that light. But image is not formed. Can you see the flame of the candle there? Yes, guys, can you able to see the flame of the candle on the screen? No, right? So that is why no image on the screen. Then it will be virtual image, not a real image. So let us see here. See, the image is formed in the lens itself. Then it is a virtual image. It is erect, means straight, and it is a magnified, a very big image. Here you can see it. And it is on the same side of the object. It is not on the opposite side. Okay. So this is about the image formation by what? By convex lens. Okay. Next we have is image formed by concave lens. Convex lens we saw where at the middle it will be broad, at the edges it will be thinner. In the concave lens, in the middle it will be thinner, at the edges it will be broad. So here in the concave lens, we have two case studies. One is when the object is at infinity, very far distance, we don't know the exact distance. So when the object is at infinity from the concave lens, the image is formed at focus 1. So here you can see, so these are parallel rays of light which are parallel to the principal axis. So they are getting refracted here. Here you can see the refracted rays. Okay, fine. So when these refracted rays are pulled back, they appear to come from a point that is nothing but a F1. Okay, and on the same side of the lens, it is on the same side of the lens from which side? That is from which the incident rays are passing. And here the object is formed here, which is virtual because it is formed on the same side of the lens. Okay, it cannot be obtained on a screen. And it will be erect. Erect means what? Straight. That is, if it is AB is the position of the object, then the image position will also AB, not BA. Okay. Then diminished means very small. This is first case study. The second case study is when the object is between infinity and the F1. We kept the object between infinity, that is between a far distance, and the F1. So this is the object you are seeing, right? So here what happens? Let us name this as the tip of the object as AB, right? So one ray of light is coming from here, which is acting parallel to the principal axis, and it is getting refracted like this. One ray of light is passing through the optic center and getting refracted, means there is no change in deviation. So when these refracted rays are drawn back, okay, they will appear or they will appear to meet at a point. So that is a point where image is formed. So here also the image is formed on the same side of a lens. Which side? On which side the incident rays are passed, no? On that side only the image is formed. So when you see the image, you can see, guys, it is very, very small compared to the object, and it is erect. Means what? See, the upper one, that is that arrow is showing. Okay, arrow mark, the tip of arrow mark is there, and the bottom one, the line is there. So it is erect. It is straight like the object. AB, this is also AB, not ulta. It is virtual, cannot be obtained on a screen. It is formed on the same side of the lens. It is diminished, means smaller than the object. So this is about the case studies of what? Concave lens. Case studies of concave lens. Okay. Then we have, so how we had the sign convention in spherical mirrors, no? Like that, we have a sign convention for spherical lenses. So here you can see the sign convention of spherical lenses is the same as in spherical mirrors, except that the distances are measured from optical center. But in spherical mirrors, what happened? The distances are measured from the pole. But here the distances are what? From the optic center, from the center of a lens. So, the focal length of a convex lens is positive. Always remember, the focal length of convex lens will be positive and the focal length of concave lens will be negative. Convex lens is positive, concave lens is negative. And same, direction of incident light, that is object distance, will be negative because it is on the left side. If the image is formed on the right side, then it will be positive. So in case of convex lens, if you remember, the images will be formed on the right side. Means that is on the other side of the lens. So the convex lens focal length will be positive. But when you consider the concave lens, the images are formed on the same side of the lens. That is on the right side, left side itself. Left side itself. That is why it is the focal length of convex lens will be negative. And you know height which is upper side it is positive, which is below the principal axis, it will be negative. Yesterday I explained it well. Okay. Next. Then we have, as we had the mirror formula, no? Like that only we have lens formula here. So the lens formula for spherical lenses, it gives the relationship between image distance. V is image distance, U is object distance, F is focal length. So in the lens formula, it was 1 by V plus 1 by U gives 1 by F. But in mirror lens formula, it is 1 by V minus 1 by U gives 1 by F. Same way, magnification produced by spherical lenses. So there also we studied magnification produced by spherical mirrors. So it is given by height of the image by height of the object. HI means what? What is the height of the image? HO means what? What is the height of the object? Fine. Then the magnification is also related to the object distance and image distance. Here we can write V by U. But the magnification of spherical mirror is minus V by U. What is V? Image distance. What is U? Object distance. So this is about the lens formula. Okay. Then we have is power of a lens. What is this? Power of a lens. So what is the power of a lens? For example, some of you will be having spectacles like me. So the spectacles will be having some power. So everybody will be having different power lenses here. So the power of a lens is a reciprocal of its focal length. So if the focal length is, let us consider the focal length is 20 centimeter, then the power of lens will be 1 by 20. If focal length is 10 centimeter, then it is 1 by 10. You have to calculate and keep it. Fine. And the SI unit of power is what? Dioptry. Means international unit. Okay. Like mass, weight we have kg. Then length we have meter. So like that, SI unit of power is dioptry. Then 1 dioptry is the power of a lens whose focal length is 1 meter. So they will ask, define 1 dioptry. Means what? When the power of when the focal length of a lens is 1 meter, then we can say the power of the lens will be 1 dioptry. Okay. Then the power of a convex lens will be always positive. The power of a concave lens will be always negative. Because concave lens, where the images will be formed on the same side of the lens. Focal length will be, the focal length of concave lens is what? Negative. So 1 divided by anything, that is minus 3, it will be, so let us take minus 10, it will be minus 0.1 p. So the power of concave lens is negative because its focal length will be negative. The power of convex lens will be positive because its focal length will be positive. So this is about the power of lens. Okay. So here it is about the spherical mirrors and spherical lenses. In the upcoming session, we are going to discuss a few concepts on light, as well as we are going to solve most important problems based on this chapter. Okay. So please don't miss the next session. Okay. Fine then. Meet you all in the next session. Until that, take care. Have a nice day. Bye-bye.